Hi, my name is Aneta and this is Chemistry at Glance. In today's video, we are going to do some questions on atom economy and percentage yield, concentration of solutions, and acid-base titration calculations. If you're not familiar with these topics, I will have a link in the description box below with my blog page where I explain this topic and many others. So let's start with it. First question. Sodium carbonate can be manufactured in a two-stage process as shown by the following equations. Calculate the atom economy for the production of sodium hydrogen carbonate in equation number 1. So first of all, what is an atom economy? It shows you how efficient the reaction is. So to calculate atom economy, you have to do mass of required product. So the mass of product you want to find. So you want to find how efficient making of this product is over the mass of reactants, all reactants, and then times it by 100. So you can put the mass as the MR, that's absolutely fine. So that's what we're going to do in this example because we don't have any masses in grams. So the MR of the required product. So we want to find the atom economy for sodium hydrogen carbonate, which is right here. So what we're going to do is find the MR of sodium hydrogen carbonate. It's 23 for sodium, 1.01 for hydrogen, 12 for carbon, and 16 times 3 for oxygen. This gives you 84.01. Now we want to find the mass of all the reactants, so the MR for all the reactants. So you've got 2 sodiums plus 2 hydrogens plus 2 carbons plus 2 times 3, 6 oxygens. And all of this gives you 137.55. So, going back to our atom economy equation, you've got the mass, so the MR of the product you want to find the atom economy for, the mass of all the reactants, so MR of all the reactants, and then just times it by 100. So the atom economy for producing sodium hydrogen carbonate is 58.5%. Next part of this question says, use both equations, both these, to calculate the maximum mass of Na2CO3, which could be obtained from 900 grams of sodium chloride. So, you want to find the maximum mass of this. So this is our question mark. And you know we've got 900 grams of sodium chloride, which is right at the top here. So what you want to do first is calculate the number of moles of this. If you do this type of question, you usually have to find the number of moles because that's what you're working with to find the ratio and so on. So number of moles of sodium chloride would be mass over MR. It's 900 over the MR of sodium chloride is 23 plus 35.5. Oh my gosh, I can't write. And this gives you 15.38 moles. Because Na2CO3 is formed from this, and this compound is the result of this equation, you want to know that the number of moles of this is the same as this, because it's a 1-to-1 ratio. So NaHCO3 has a number of moles of 15.38 as well. This 15.38 moles has been used now in this equation. This 15.38 is 2 NaHCO3. And now the ratio between this one and this one is 2 to 1. Because we got 2 moles used here, and that was only one, there was only 1 molecule of this, and now we're using 2 molecules of this, you would have to times it by 2. It's 30.76 moles. And now we want to find the mass of this, and we got 2 to 1 ratio. Oh yeah, sorry. Of course, there must be confusion. You don't have to times it by 2. This is what I meant. It's kind of difficult to understand, but I'm going to try my best. So this amount of moles, 15.38, is the same in here, but this equation just shows you the ratio between this one and this one. So you still have the same amount of moles, which is 15.38, because it's the same thing, but now in this equation it shows you the ratios of these, which is 2 to 1. So this is 2. To find the n of this, you have to divide 15.38 by 2, which gives you 7.69 moles of Na2CO3. I know this may be confusing, and you will want to just times that by 2 because it's 2 in here, just like I did before. But this amount of substance right here is the same as this one. But now it shows you the ratio between these. So this is the number of moles for Na2CO3, and the MR of this is 23 times 2 plus 12 plus 16 times 3. So to find mass, it's N times MR, which is 7.69 times 23 times 2 plus 12 plus 16 times 3. And this gives you 815.4 grams. And the next question. When 1 kilo of sulfur dioxide is reacted with excess oxygen, this means you don't have to take oxygen into consideration because there will be enough of oxygen for the reaction to be complete. 1.225 kilos of sulfur chloride is formed. This is the equation, and now we've got to calculate the percentage yield. So in order to calculate the percentage yield, you do the actual mass you received from the experiment over the theoretical mass, so the book mass, so the one you should get, times it by 100 to actually see how efficient it was, the experiment actually was, if it's going to be the same as in the book. So you want to find a percentage yield. So the actual mass you got from 1 kilo of sulfur dioxide is 1.225 kilograms. Sorry, it's sulfur trioxide, not chloride. Sorry, I've made a mistake there. Trioxide. So the actual mass you got was 1.225 from 1 kilo of sulfur dioxide. Now you've got to find what the theoretical would be. So if you had 1 kilo of sulfur dioxide, finding the N, mass over MR, 1 kilo over the MR of sulfur dioxide, which is 32 plus 16 plus 16, because we have 2 oxygens. And this gives you 0.0156. So knowing this and our equation, it has a 2:2 ratio. So the N for sulfur trioxide will be the same. So we're just trying to find a mass, which is N times Mr. Mr of this is 52 plus 16 plus 16 plus 16. And this gives you 1.2496 kilo. So this is the actual mass that we should get, but we actually got a smaller mass. So percentage yield is this over the theoretical mass times by 100. And this gives you 98%. The high percentage shows you that the mass you actually got is very similar to the mass that you should get, which is good, because that means the reaction was effective. So our next question, 25 centimeters cubed of 0.2 moles of sodium carbonate solution was neutralized by 20 centimeters cubed of dilute hydrochloric acid. Find the concentration in grams decimeters minus 3 of hydrogen chloride. So this is our titration question. So during titration, you know the volume and concentration of one solution, and you're trying to find the concentration of the other solution, for which you also know the volume. So in order to do this, we've got sodium carbonate, and we've got the concentration and volume of this, so we want to find N. This is our equation that we're going to use here. Concentration is 0.2 times the volume, but it's in centimeters cubed, and it has to be in decimeters cubed, so we times it by 10 to minus 3, because centimeters to decimeters is times 10 to the minus 3. This gives us an answer of 5 times 10 to the minus 3. Now, we know it was neutralized by 20 centimeters cubed of dilute hydrochloric acid. We got hydrochloric acid right here. The ratio between this and this is 1 to 2. So 1 mole of this is needed for 2 moles of this. So you gotta times our answer by 2 to give us 0.01. And this is the number of moles for hydrogen chloride. So if we know the number of moles, and we know the volume, which is 20 centimeters cubed times 10 to minus 3 to decimeters, we can use again this equation, but rearranged, to find concentration. And this concentration is 0.5 mole decimeters minus cubed. However, what we also see is that they want us to find the concentration in grams decimeters minus cubed. In order to change from molecules decimeters minus cubed to grams decimeters minus 3, you've got to times it by the Mr. And if you were going the other way, you would have to divide it by the Mr. You don't get this in the data booklet, but you do get this in data booklet. So this you've got to remember. So our concentration, we have to times by the Mr of HCl, which is 1.01, plus 35.5. And this gives you 18.3 grams decimeters minus 3 as your answer. Next question, it seems like a big question again. So, 0.497 grams sample of ground limestone was placed in a flask, and exactly 25 centimeters cubed of HCl of concentration of 0.515 mole decimeters minus 3 was added. The mixture was stirred until normal bubbles of CO2 formed. The unreacted acid in the flask was titrated against 0.188 moles decimeters minus 3 sodium hydroxide and required 24.8 centimeters cubed for neutralization. Calculate the number of moles of HCl used up in the reaction with limestone. So, to explain the question, limestone with acid were mixed together. Then, the acid that was left was reacted with sodium hydroxide again to be neutralized. So, we've got to work backwards. So, at the end, this amount of sodium hydrogen of this concentration had to be added. So we want to calculate the N for this. Times 10 to the minus 3 to change it to decimeters. And this gives us 0.0129 moles. We also know that at the very beginning, it was that amount of hydrochloric acid with this concentration. So we want to find the N of this as well. Times 10 minus 3 decimeters. I'm sorry. This is the answer to this. And the answer for this one is 4.66 times 10 to the minus 3. Sorry about the confusion, but what you got now in here is the number of moles of hydrogen chloride you had at the beginning. And this is NaOH has the same ratio, it's 1:1 ratio to HCl because it's not said otherwise. That's what we got to consider as that. So 4.66 times 10 minus 3 was used to neutralize hydrogen chloride. So this means that amount of hydrogen chloride was left after the reaction with limestone. This was at the beginning, this is what was left. So what you got to do is take this away from what was at the beginning. And this gives you 8.24 times 10 to the minus 3 moles. This is the amount that was used with limestone. Part B, calculate the percentage of calcium carbonate in the limestone sample. So we know this amount of hydrogen chloride was used with limestone. Was actually not used, because more hydrogen chloride was used. But this amount was actually is the amount that actually reacted with limestone. So that's what we're going to focus on. So the calcium carbonate, got to find percentage of calcium carbonate, and it has a 2:1 ratio with hydrogen chloride, and we know the N for this, which is 8.24 times 10 to the minus 3. So you have to divide this by 2, which is 4.12 times 10 to the minus 3, and this is the number of moles of calcium carbonate. So we've got number of moles, you've got the MR because you can calculate it, so you can find the mass. 4.12 times 10 to the minus 3 times calcium is 40.1 plus 12 plus 16 times 3. So the mass of calcium carbonate is 0.412 grams. This is the amount of calcium carbonate, and this is the amount of limestone that was placed. So to find the percentage of this in this, you do 0.412 grams over 0.497 grams, times it by 100, and you get 82.9%. So this is a percentage of calcium carbonate in limestone. And our last question, hydrogen can be produced by the electrolysis of brine, which is concentrated sodium chloride solution. The overall equation is as follows. And then we have to calculate the atom economy for hydrogen. So the MR of hydrogen is 2.02 because we've got 2 of them. The MR of all the reactants equals 2 sodiums plus 2 chlorines plus 4 hydrogen plus 2 oxygens. And the overall for this is 153.04. So to find the atom economy, you do 2.02 because you want to find atom economy for hydrogen over all the reactants and times by 100 to give you 1.32%. So the atom economy for hydrogen is actually very, very small in this equation. B. Hydrogen can also be produced by the electrolysis of water. The equation is as follows. And now we've got to find the atom economy for hydrogen in this equation. So we've got 2 hydrogens. 2 hydrogen 2. So we actually got 4 hydrogens, which is 4.04. This is the MR for hydrogen. Now we've got to find the MR for reactants. This is just water. So you've got 4 waters plus 2 oxygens. And this gives you an answer of 56.04. What we do next is, as before, you want to find the atom economy of hydrogen, so 4.04 over 36.04 times by 100, and this gives you 11.2%. This is slightly bigger than this one, but still quite small, I would say. So the last part says, explain which of these 2 processes is more efficient for producing hydrogen gas. So more efficient would mean a higher percentage. High percentage would mean it's more efficient. So this one is more efficient than this one because more hydrogen gas is produced by this equation, by this reaction, than by this reaction. So the second method is more efficient because a higher percentage of atom economy is present, therefore greater amount of hydrogen gas produced. Hydrogen gas was the aim of this, so the second process created more hydrogen because the atom economy is higher. And these were all of the questions. Remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I leave all the links in the description box below. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Thank you. Like, subscribe, and see you soon. Bye.